science that we don't struggle with, but in science we need to be able to, I call it telling the truth. I have an example here. So, tell the truth. So this is rice, obviously, and if I were to say, okay guys, count these rice grains, you'd be like, oh, whatever. So you might do one of the things that I did, and this is, I'll pass this around. This is 10 rice grains. Okay, you could get a mass of this, okay, and then scale it, then get a mass of this. Okay, so this is 10 rice grains, and I'm pretty sure that's what I did for this one, because this is, I have approximately 1,000 rice grains in here, and I didn't count those. Okay. So I was kind of thinking about that. So if I go back to this, let's say you have not just this amount, you have like a pillowcase full of rice grains, and you're supposed to count them. And if we do that method of scaling up how much 10 weigh to how much our quantity in question weighs, there probably would be some error with that. Don't you think all rice grains they're maybe not all the same, so the mass is a little bit different? So we could actually test that. And so let's just say with our technique, we can measure 100 rice grains plus or minus, let's say, 30 rice grains. So in other words, if I say 100 rice grains, then I can either have what? 70 rice grains to 130 grains. Okay. That is, that's sometimes called a tolerance. That's just kind of inherent in how I've chosen to count rice grains, because I don't want to be here forever counting rice grains. Okay. So does this make sense that the closest you can kind of get to it is, how do I say this? Well, let's put it this way. If somebody says, I counted rice grains using my technique, and I came up with 1,352 grains, does that kind of defy your common sense a little bit? Because how do you know this? Are you really telling me you know it to the nearest grain? When you tell me that the tolerance in your method is plus or minus 30? Yeah, I'm cool with that technique, but you have to be realistic about the number, the measured quantity that you put forth. What's that? Oh.
I was just trying to get you want to see your price.
So I kind of put a question mark over the 2 in 1,352. Usually when you give a measured quantity like this, that last digit, that's where the play is. Okay? So honestly, I think based upon this tolerance up here, I think you're going to have play right here in the tenths place, because it's plus or minus 30. That's my point. Okay? So, need to talk a little bit about, let's say you think you got the right answer, and maybe you did get the right answer. Okay? And there are times in the lab and in chemistry when we have a true value to compare your answer to the true value. So how close you are to the true value is accuracy. Precision is if you're in the lab and you're doing an experiment or gathering some data, if you were to start from scratch and do that same process again, would you come to the same number? I know you're like, really? So basically, whatever you do in the lab, you do it multiple times, and do you get the same answer? Okay, that's precision. And it really kind of lends itself to the classic dartboard. So where are you trying to, when you're throwing darts, where are you trying to get? In the middle. So that's your true value. Yep. So are these very much in the middle?
Unless you're not playing that game. Different game than you're not trying to.
Oh, that's true. It would be a different game. Okay, so this is just a normal game. So that's why it says accuracy kind of sucks. And precision, that I think, like if you throw darts, if you can control it and get repeatably at the same place, that's high precision. This guy's got a lot of scatter, this guy's got a lot of scatter. So poor precision, poor accuracy. Well, these are clustered, and assuming you're playing the game where you're trying to get the center. So they're really tightly clustered, so the precision's great. but not getting it in the bullseye. So the accuracy sucks. Okay. And then last but not least, they're nice and tight. So it's very, what we say, reproducible. The precision is great. They get the same answer, same location, and it's accurate. So accuracy and precision are great. I guess I would argue there's one more scenario, and if this is another dartboard, okay, you know how you can like do let's see, perform a calculation multiple times, and then like if you do it 5 times, you just take the average. So for instance, what if I did it 5 times, and I got the bullseye once, I got it up here in the upper right once, lower right once, upper left once, lower left once. And to me, just kind of visualizing where is the middle of those. It's in the bullseye. So to me, that's one more scenario. What's the precision here? Is it good or bad? Are they? What's the precision here? It's bad. Yep, poor precision. Yep. But if we are going to go ahead and average those 5, where is the average of those 5? Just kind of eyeballing it. In the middle. So if you're taking the average of those 5, what do you think? What's the accuracy?
Good accuracy.
What's that?
Would be good accuracy with the average value, but
Good accuracy with the average value. Yep. So that's, I guess, one other thing I would say. So high accuracy. If you're taking the average value, that's what you call lucking into the right answer. Okay. So error, like how much off you are. Now, it might be kind of hard from your perspective to say, well, what would you know what the right answer is? But like I said, in chemistry, there's thick books of properties of matter, for instance. You can go ahead and compare your experimental value with the actual value and see what the error is. Uncertainty, sometimes I call that wiggle. Okay, the uncertainty. When I showed you a minute ago the example of the rice grains, the wiggle there, the uncertainty was plus or minus 30. Okay, so that's kind of our scatter, right? And that's associated with precision. So error is how far off you are from the real value. A lot of times it's just a quick subtraction. And then uncertainty is kind of, you can also measure it from the average, how far off your individual values are. That last example where I had a bullseye in the middle and then I kind of hit the 4 quadrants, okay, in that case, our uncertainty was pretty high. If we were to do what's called a standard deviation, take basically, find the average, which was in the middle, and then get the difference between each value and the average, that would be pretty bad. Okay. All right. So error is the difference between what you got and what the known value is. Absolute error, then, is just that simple subtraction problem. Okay. Relative error is a little bit different. Relative error is, and I think we'll probably do this in one of your calculations down the road. Relative error is you do the subtraction. So you have the measured value up here. Let's do it this way. Absolute error is you have the measured value, MEAS for measured value. From that, you subtract the best value. I'll just put best. Okay, that is your quick subtraction for your absolute error. Relative error, then, is you take the measured value. You do the same, you start the same way as absolute value. Measured value minus best divided by best. And sometimes best I'll say is actual, and sometimes measured value I'll call it experimental. So how well did you do? So all quantities that you measure, so like yesterday when you got the lengths and stuff with your rulers, there was wiggle in that. And actually the wiggle was the last digit that you put down, which hopefully was what, the nearest hundredth of a centimeter? That's where your uncertainty lied. A lot of times what they'll do is they'll go, like if you got 12.57 centimeters, okay, I'm going to go ahead and put a question mark over the 7 in the hundredths place, okay? And a lot of times the convention is to just to go plus or minus 0.01 centimeters, kind of like I did with the plus or minus 30 grains. Okay, so that's kind of like the tolerance. So there's uncertainty in all measured quantities. That's like when I don't know, if you tell your kids to be home in 30 minutes, do you mean 30 minutes plus or minus 10? Do you mean 30 minutes plus or minus 1 minute? Okay. I don't know what kind of mother she is. Well, I try. We've got one still at home, so she's a senior. But there's wiggle room in the time. That's my point, that you tell a person. Okay, so remember in yesterday's lab, I kind of put two things up on the board. I put multiplication, division, and I said round according to digits. And then I put addition, subtraction. I said round according to decimal places or tens places. We're kind of building up to that. Now, when I said round according to digits, what I really should have said, or could have said now, round according to significant figures. Significant figures. That's your digits that you can count. So this simply says, remember the question marks I've been putting down? And I can't remember, like I said 12.57 centimeters. And I put a question mark over the last digit. You can keep only one uncertain digit. So that's to say that my 5 is certain, my 2 is certain, and my 1 is certain. In the tens places, in the ones places, and in the tenths places, that is certain. My wiggle comes in, my uncertainty enters in the rightmost digit. Okay. So yeah, oh my gosh. So if this is like measuring mass or something, that's a really expensive piece of equipment. So if somebody says something weighs 4.1267 grams, okay, that means it's plus or minus 0.0001 grams. As you might imagine, the more persnickety or the more precise a balance is, the more it costs. So there's uncertainty, and now instead of a question mark, you're going to see on my slides just turn red hot. So the red hot means like a question mark. That's where the play is. So the first part that's blue, it's not red hot, is exact. I know for sure, beyond a shadow of a doubt, it's at least 4.126, but not sure about the 7. Like I said, usually it could go plus or minus 1, but not necessarily. If you buy equipment, the measuring equipment that you buy will tell you kind of what the uncertainty is or the tolerance of that equipment is. So the last digit is uncertain. So kind of be thinking along that lines. Okay. So our balances are digital. Now this is an analog balance. And if you're like me, I have to kind of read it, concentrate. We have gradations on this balance. It just doesn't spit back a number like our balance. So these gradations are each 1 gram. And remember, I told you in lab, and we're going to stick to that, every time you have gradations like this, what you have to estimate between the gradations. So this person simply estimated between these gradations right there and said, oh, it looks like it's about 2/10 of the way from 1 to 2 grams. So that's why they said 1.2 grams. So that works. Well, here's a different kind of balance. Again, it's an analog, not a digital. I guess an analog, it's not analog. But it's definitely not a digital. We used to use these balances. I've used these balances before. And the way you read it is the 1 is the gram. Notice what we're making here, a pistachio. Makes you hungry? And then the 2 is the grams, and now we have marks to the nearest tenth of a gram. So that's kind of why it's similar to your rulers, that you have to push it. Now, we know for sure it's 1.1, 1.2, and where we're estimating is between 1.2 or 1.3. So notice what this person did is, it looks like a little on the other side of half. So 1.26 grams. This is kind of consistent with what we talked about yesterday. So there's some numbers, and they're measured numbers, that there's no wiggle room in them. Like I could count people in this room, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 people in this room, right? And that's not too hard, because like, there's nobody hiding, and there's no...
not half a person in here.
There's not a half person in here, right? It's not plus or minus 1, okay? So that's going to be important. Exact numbers are important. We're going to talk more about that on Monday. But there's no uncertainty there. So I say 9, no hot numbers. The other type of exact number, not by counting, is by definition. And we've talked about a few of them. Do you remember, I told you need to memorize 1 inch is equal to how many centimeters? 2.54 centimeters. Very good. And then when I did that, I said that is an exact relationship. And not all those other equalities that I said between the English and metric system on that one slide, I had one for weight and one for volume. Those were approximate. This is exact by definition. So there's no uncertainty there. And there's also no uncertainty. Let's see how we're doing with the metric system. Can we talk a little bit about the metric system? Let's see. 1 kilometer is equal to how many meters? What do you think? 1,000. Yep. You got it. And that's also exact. And it's also exact for the same reason 1 inch is exactly equal to 2.54 centimeters. That's by definition. Okay, so exact numbers by counting or exact numbers by definition. All right. So by counting, what we're looking at, yep, 7 pennies. Right, no uncertainty there. Another exact relationship, 1 foot is exactly equal to how many inches?
12 inches.
Good, yep, 12 inches. Yep, it's by definition, no uncertainty. You got it. Okay, so we'll do a lot of multiplying and dividing when we get going with our chemistry problems, a lot of multiplying and dividing. When we're multiplying and dividing, I told you yesterday, you hone in on the number of digits in all of the things that you multiply together, and whatever measurement had the fewest digits, those fewest digits is what you round your answer to. So I need to talk more about counting digits, counting significant figures. So first off, if you're looking at a measured quantity and you need to count significant figures, if that digit is not 0, put a check. It counts as significant. So an example of that would be like if I had 12.34 centimeters. I'm going to put a check over all significant figures, significant digits. And then I'll put a little number there, how many there are. So they're not 0, so they count. The zeros are what get us. So I'll show you an example of the zeros. So what if I changed it up? And what if my measured quantity was 12,057.2 grams? Okay, so according to the first rule, I'm going to count the 1, the 2, the 5, the 7, and the 2. And according to this rule, I'm going to count that 0 that's nested between the 2 and the 5. So we're looking at what, 6 there? So here's another one for you. Trailing zeros after the decimal are significant. And I'm going to try to kind of prove that to you with an example. So an example of that would be 102.300. Let's make it pounds. All right, so let's count. I got the 1, the 2, and the 3 according to the first rule. I got that first 0 according to the second rule. Now, does this make sense that these, the way I think of it is somebody really wanted to portray something about the measuring equipment by putting those zeros there. It took effort to put those trailing zeros there. So what would the kind of the tolerance of this device be? Plus or minus 0.001 pounds. Okay, they are significant. So according to this rule, those are trailing zeros after this decimal. Trailing zeros after the decimal. So I got what, 6 again? Cool. Now this other type of 0, I have actually 2 more types of zeros a little bit. This type of 0 is important, but these zeros are what I call placeholders. If you want to put placeholders there, and you'll see what I mean. That's what I call them anyway. These are placeholders. Okay, so leading zeros, let's see, leading zeros after the decimal. After decimal. Here's what I mean by that, leading zeros after the decimal. So they're leading zeros. So here I'm going to go ahead and put, it's a very small number. This only works for very small numbers. I'm going to put 0.000. Those are my leading zeros after the decimal. 392. Okay? So here's what I mean to say. I'm going to put an X over these first 3 zeros. They're placeholders, they're important. Okay, but when I show you, like I said, I'm going to try to convince you of this, but if you're not convinced, that's fine. But they're not significant with regard to relative uncertainty. So the 3, 9, and 2, I'm going to count those. And I'm back to 3 sig figs. Any questions about that? Students sometimes will ask me, and maybe you can answer this, what if I went ahead and threw 1 more 0 up there? Would that be significant? How many people think it would be? I do too. Yeah, that would be significant. Yep. I'm going to revisit this last one here in a minute. Now, if I were to write the number, let's see, 5,650 inches. So where is my decimal in this example? Yeah, my decimal is after the 0. Now there's a difference between what we all know that is actually an implied decimal. Implied means nobody took the time to put it there. We all know it's there. It's implied. So what I usually do for an implied decimal is I'll put it there and I'll kind of put little dots around it to show that no one put it there, but we all know it's there. It's an implied decimal. Okay? So I'm going to kind of talk about that, but if no one really took the time to put it there, actually the convention is to go with plus or minus, in this case, 10. If no one cared to put it there, we're going to think that the uncertainty begins here. I'm going to make that digit 5 in the tens place red hot. And if that's the case, then, you know, we don't count that. That's probably, it's what we say ambiguous. We know it's implied there, but no one put it there. Okay. So now you guys get a chance to go ahead and do the next one. Count significant figures for those. Right here. Count your sig figs. And that's what your homework for Monday is going to be. When you got them done, go ahead and take a look at the board, make sure you got them right. Any challenges for those? Any questions? No. So again, just to kind of connect this up with what we did in the lab yesterday, when you're multiplying or dividing, these are the digits you're counting. Any questions? No? So here's where I get to try to kind of convince you of the zero thing. So I told you, was it the third rule? That the trailing zeros after the decimal are significant. So how many sig figs in 2.5? Yep, I agree. And how many sig figs in 2.50? 3, yep. Sig figs in 2.500? 4, yep. I'm going to show you why that is. So if we go with kind of the uncertainty or the tolerance as plus or minus 1 in the last place. 2.5 is plus or minus 0.1. 2.50 is plus or minus 0.01. 2.500 is plus or minus 0.001. And if that's our uncertainties, okay, if we go ahead and divide those uncertainties, if we divide, those uncertainties by the value, and if you're like me, where did that 25 come from? Well, this 25 came from dividing 1 over 25, excuse me, by 2.5. If you divide 0.1 by 2.5, does that equal 1 over 25? Okay. In this one, we said that the uncertainty was plus or minus 0.01. If we take, go back. If we take 0.01, are you serious? It only does what you ask it to do. If we take 0.01 and we divide that by 2.50, move the decimal place over, bless you, that's equal to 1 over 250. And last but not least, if we take 0.001 and divide that by 2.500, move the decimal place over 3 places, we get 1 in 2,500 parts. So these actually are relative uncertainties. And relative uncertainties, I know I butchered that there, that word's uncertainties. The relative uncertainties are important because they're kind of telling you the play in the measurement overall. And that only came from putting those zeros there. So that's my convincing you that trailing zeros after the decimal are significant. Okay, so the placeholder zeros, the like for the placeholder zeros only work for very small numbers, like the 0.000392. So those placeholder zeros are not significant, and I'll try to show you why that is. So in all of these values, 25, 2.5, 0.25, 0.025, 0.5025. Hopefully you guys would tell me there's two significant figures in all of those. And I'm not going to do it, but we could do it. If we go ahead and for each one of these, do what we just did a minute ago for the trailing zeros, plus or minus 1, plus or minus 0.1, plus or minus 0.01, you kind of get the idea. And this would be plus or minus 0.000. We got 5. Okay. If we were to go ahead and do the ratio that we did before, you would come up with, in all these cases, the relative uncertainty is 1 in 25 parts. So, although these leading zeros, that's a leading zero, although those leading zeros are important, you can't blow them off, they don't add any, they are not significant. All right. Okay, let's revisit that last rule where the implied decimal. So you guys would tell me that the decimal goes here at the end of the zeros. But nobody put it there, so it's implied. And we don't know whether that's really plus or minus 1, okay, plus or minus 10, plus or minus 100, heck, plus or minus 1,000. We just don't know where the wiggle is there. So in general, these rules of rounding are, if you go with conservative, you're in good shape. So in general, we're conservative. So on the previous example, 32000 with an implied decimal, you're always conservative, so you're only going to give it 2 sig figs. Okay, so that's it. That is it. Now, this is no longer an implied decimal. This is a hardcore, somebody put it there. That changes everything. If somebody does that, then they mean that actually the uncertainty begins in the ones place. So in that case, there, like this said, there are 5 significant figures. Bless you. So this is not an implied, this is explicit. Explicit is the word, decimal. Okay. And of course the 3 and the 2 count, and now these zeros count too. Okay. So here's what I already told you a minute ago, that in general, with the 32,000, there's only 2 significant figures. Okay. So you guys did homework today, kind of playing around with scientific notation. And the reason we need scientific notation in chemistry is we are dealing with really big numbers, like how many rice grains there are here, okay? And really small numbers, like the mass of an atom, okay? So we need scientific notation to pack those up. So scientific notation, you guys know, has a coefficient part, the decimal part, and the exponent part, 10 raised to a power. So the coefficient part is what, let me just go to an example. The coefficient part right here, in this case 3.2 is the coefficient part, actually tied into there are the number of significant figures for this measured quantity. So if it's packed up in scientific notation and you need to count significant figures, you just look at the coefficient. That's it. So this is that 32,000 again. So if I needed to write 32,000 and show 3 significant figures, I could pack it up in scientific notation and show 3 significant figures in the coefficient. And that works. So 3.20 times 10 to the 4th, it's the same number, but now the 3.20 gives me 3 significant figures. And if I needed 4 significant figures, I could put another trailing 0 after the decimal in my coefficient. Okay? And this just seems silly. 3.2000 times 10 to the 5th, or sorry, times 10 to the 4th. Of course, that gives you your 5 significant figures. I think instead of doing that, if I know I needed 5 significant figures, I would explicitly put the decimal, like I was talking about before. Okay, if I really put it there, instead of just implying it, then I'm back to 5 sig figs. Okay, so I don't know if I convinced you about how significant figures work, but I'll tell you, as much as even your first unit exam, I'm going to be holding you accountable to rules that we talk about, counting sig figs, on Monday. So for now, though, these will be due on Monday. And actually, I have a screenshot of these. I notice these are all even problems. Like, dude. Yeah. You'll do fine. So we've been talking about counting significant figures. You need to count significant figures in these. Oh, wait. For each measured quantity, underline the zeros that are significant and draw an X through the zeros that are not. Oh, so let's follow the rules. Okay. For this one, how many significant figures are there in each quantity? I think you'll do okay there. For this one, notice here on the left we have some measured quantities that have uncertainty with them. And here on the right, somebody's gone and counted significant figures in that value. So you're supposed to correct any values in the table that are wrong. If there's nothing wrong, leave it. That's a little game we play. And then last but not least, this one. And we talked a little bit about rounding in lab, but your directions for 50 are to go ahead for each of these quantities, give only 3 significant figures. And I think I mentioned this, but when you're rounding and you have to round to a certain number of significant figures, you start at your left and go to your right. So I just threw up 53.2159. So I'm only allowed 3 significant figures. So I'm going to start at the left. I'm going to take those first 3. So I truncate it there after the tenths. And so since that's a 1, what am I going to do with the 2? Am I going to leave it or round it up? Just leave it, yep. Exactly. So I would rewrite this with 3 significant figures as 53.2. Okay? So that's your whole numbers thing. And have a great weekend, everybody.